We have a system of pulleys. We have two pulleys and a frame. It's generally a frame. Let me just write the problem statement. And I want to look at the free body diagrams for the whole system and each part separately. So let's just phrase it this way. For the frame, and it's not moving, so we can probably easily guess that's a frame and it's not a machine. Draw the, let me get it right, free body diagram of the entire frame. So that's one thing to do. First, draw the free body diagram for the entire frame, which let me write it fully, including, that's not, including pulleys and cords. Pulleys and cords. Second thing is draw the draw the free body diagram of the frame without, I think that's what it says, the pulleys and cords. Exclude those. And finally, draw the free body diagram of each pulley. Right. All right. To start from the first part, draw the free body diagram of the entire frame. Let's draw it. I'll do my best. Let me do it here. So this is the frame. Let's say I have this one right there. I have this one right here. It includes everything. So let's just assume that this is the pulley as good as I can draw it. And that is not the pulley. Pulley is supposed to be here. There we go. And the other pulley there. I can move this one way or another, hopefully, or I can't, and I just move it this way. As much as I can do the trick. There you go. All right, accept it for me. All right, free body diagram for this, right? And we have the ropes there. So we're taking into account the whole system. So I'll draw it like this right there. And draw it like this. But keep in mind, I'm isolating the whole system. So whatever is this line cut has to be taken into account. All right. So what do we got there? We have the tension on this cord. We are given that is 75. Let me use the proper color. 75 pounds. What else do I have there? Can someone tell me at least one of support reactions? Thank you, Colin. Exactly. We have support reactions there. And I'm just going to choose some arbitrary direction, just positive, since we don't know about these. That would be AX, and this would be AY. Anything else? Tension on rope attached. Exactly, Daniel. So we have the tension on the rope. There you go. And let's just call this TD. That's pretty much it. That's all the forces that I could see when I isolate the whole frame and draw the free body diagram. These are all the forces I could put there. So this would be the free body diagram, for entire frame. Right. Let's go to the second part. So draw free body diagram of the frame without the pulleys and cords. All right. Let's see how does that work. I'm gonna draw the frame somewhere right here. Right, I have this one, and I have this one. All right, so now what is happening is that, well, I'm looking at this frame. If you think about this frame composed of this metal part, that is the whole structure there attached to each other, this part, and this pulley there, and the other pulley here. Right? I'll take these pulleys apart, like aside. I don't want them in my free body diagram. I want the free body diagram for just this green part of the frame. This structure that is basically welded and attached to the wall. So this is what we're isolating now. Let me see if we can do it this way. This is what I'm isolating. All right. Now, what do we have there? We have, well, I already know that I have support reactions. That hasn't changed. So I'll just put them again here, AX, AY. Remember, this is a frame, so I can dismantle all the parts and look at the free body diagram of each part separately. And each part should be in equilibrium. Later on, we'll see that. But, well, you already know that. But we'll see how can you use it. But in this particular problem, I'm just interested in knowing the free body diagram of different parts. And in this part of the problem, free body diagram of this green frame. So I have the support reactions at point A. Let's see what else do we have. I can see the tension right there in this cable there that the isolation line goes through, this tension right there. And this cable's cut. So I can put a tension there. How much is the value? Do I know that tension force? It goes back to the assumption we made about the rope, right? We said exactly, right, 75 pounds. We said the force throughout a cable or a rope is constant. No matter where you look at, it's constant, right, in that rope. So that would be 75 pounds. All right, we figured that out. Good. Let's see what else do we have. Now, we have those two pulleys that we dismantled, right? We took apart. Let's just, before we go there, we have another rope there, this rope. Right? That rope was also, when we're isolating just the frame without pulleys, it's cut by this the line I draw to isolate that. So I have to put that there too. It's also, again, part of this cable. We already represented with TD. Let's just represent it exactly the same thing, TD. This is not supposed to be in blue. This is TD also. So that's TD. All right. Now, you might think we're done, but we're not done. We have connections between this part of the frame and pulleys, right? And these connections are happening at point at C and B. Right? If you clean up a little bit here, this is the isolation part. This is the part that this frame is connected to pulley, and this is the other point that the frame, this part of the frame, is connected to pulley C. Let's call them pulley C and pulley B. So if I take out that pulley, think about how that pulley is connected to the rest of the frame. Moments there, well, that's where we're going right now, right? We want to figure that out. But that's a very good question. So we have the pulley, right? This pulley, I have my pulley right here, right? This pulley can easily rotate around this point connected to the frame. Let me just, my shirt is not really helping. It's connected to a frame. Right? Imagine that this is the frame and this is the pulley at point C. Now this pulley can rotate. I can easily rotate this pulley. So there is no resistance for rotation. So what is the resistance? What kind of reaction or resistance this frame is providing, or how does this frame is preventing this pulley from moving? This pulley cannot move, cannot go up, cannot move horizontally, cannot move vertically, cannot move in any direction. Right? It's fixed there because of the frame, but it can rotate. So if I take it out, the forces, the internal forces between this part of the frame and this pulley is pretty much just forces that are preventing the pulley from having that specific type of motion, which is basically translation in either direction. So what I need to do is that think about it as a pin. Right? Remember how pin were working in a truss structure? Right? In a truss structure, pin does not really handle any torque or moment. It can only prevent the frame or the structure from moving. So that's the same story. Here, well, direction you can choose either direction, doesn't matter. But you have to replace that. If I can do that. CX, CY. Does that make sense why we do this? Because again, the pulley can rotate. So the frame is not preventing this pulley from rotating. But once I take the pulley out and I want to compensate for this missing pulley in this point C or joint C, connection C, I have to compensate for the forces interacting between these two. If the pulley is being pushed or pulled, whatever force is applied to pulley is going to transmit that force to the frame through this pin C, and that force, the transmission cannot be rotation because pulley can rotate. It's not going to transmit such force to the frame. It only prevents this from going up and down or any other direction, which whatever the direction is, I can decompose that as two components of components of CX and CY. Same story about the other pulley. It can rotate, right, connected at point B, but whatever force is applied to it, well, it can handle, or it does not transmit torque to the frame. What it does is that when I apply force to this, let's say this force horizontally, it doesn't move. It transmits that force to the rest of the frame. If I pull it this way, it doesn't move. It transmits that force to the frame. So any force with any angle applied to this, right, is going to be transmitted to the frame. Torque does not, because pulley can rotate. So if I take that pulley out, I have to compensate for it. And let's say I do it this way. Would be BX and BY. BY is in horizontal direction, obviously, as BY. Right. All right, that's pretty much it. Right? I put external forces, which in this case was 75 pounds, and other ones were all because because of the isolation either, or because of the support reaction, or the connections between that part and other parts, which were counted as internal force. Now, what if you want to draw a free body diagram of each pulley? Let's look at each pulley separately. Let's write this free body diagram for the frame without pulleys. Now let's take a look at free body diagram of each pulley. Let's take a look at pulley B. I'm just going to put it right here. I'll put B here to show that this is pulley B. So what I'm doing is I'm isolating pulley B. Well, better to say it includes, obviously, let's go straight. I'm isolating pulley B. If I do that, well, I'm taking it out. Right? Well, obviously, the rope is there. Right? Pay attention, the rope is cut in two parts, here and here. So both of them have to be taken into account. Downwards, yes, exactly. One downward, 75 pounds, and one in this direction, 75 pounds. Because both, I'm isolating just the pulley, so whatever that line goes through and I cut through it, it has to be presented on my free body diagram. Another thing is point B, right? Before I took this pulley out and I looked at the frame, now I'm going to put this pulley out and I just look at the pulley itself. Now, since it's at point B and I already put BX and BY on the frame, remember, these are internal forces. So exactly like what we were dealing with in truss structure, but it's a little more complicated here. That was the simplified version. Internal forces. So whatever force is applied by the pulley to the rest of the frame should be equal and opposite in direction of the forces that are applied from the frame to the pulley. Right? It's Newton's third law. This is in static equilibrium. It's standing right there. Right? It's in equilibrium. Pulley is not just moving around by itself. It's connected. So whatever force the pulley applies to the frame should be equal to the force that the frame applies to the pulley in opposite direction. And they cancel each other. They should cancel each other because, again, the frame and pulley are just standing there. Newton's third law. So if I want to put the forces on point B, I'll do the same force but in opposite direction. Now this would be Bx because I took Bx considered in opposite in direction to right on the that structure. Now in this pulley, I'll put it in the same along the same line of action, same magnitude, opposite direction. Same story with By. On that rest of the frame, on that part of the frame, I put it upward, positive. Same line of action, same magnitude, opposite direction on the pulley. Right? Newton's third law. That's why we write it down. Let's look at the other pulley. How about that one? Pulley C. I'm isolating pulley C. And take it out, right? Isolate and take it out. What do we got there? Same thing, right? With tensions, exactly. Go there, it's TD, and right here is TD. In this case, we don't know the tension. Exactly. Thank you, sir. Right and down. But we also have the same story at point C, right? Point C is also the connecting point. BY should be flipped, right? BY should be, it is flipped, right? On the frame, it's upward, and on the pulley, it's downward. Unless I made a mistake somewhere. They should be exactly same magnitude, but opposite direction on each of these. Because at the end, when these two connect together, they should cancel each other on the total frame. Because these are internal forces and the structure is not falling apart. So internal forces are canceling each other. Right? So whatever BY we put on the rest of the frame, we should put the opposite direction on the part that is connected to the frame at point B, which in this case is pulley. Now C, the same story. CX is to the right on the on this structure, so I'll put it in the opposite direction here. CX. Remember, the magnitude is the same, so that's why I'm using CX. So it shows the magnitude, but the direction is opposite. Newton's third law tells me that these two are interacting. If this one applies the force CX to the other one should apply force CX to this one in the opposite direction. Same story, CY is upward, so on this should be downward. Right?